Hello math30-2 and welcome to your first lesson on probability. This lesson you'll find later on is very similar to the lesson we had before with permutations and combinations. This builds up on permutations and combinations. Before we get into that, we must first look at some terminology and basics of review. So, here's some beginning terminology. First of all, a trial. A trial is an event, or a trial is one thing. So if I roll a dice once and I want a 1, like it says in the opening thing here, and it's 1 and 6, my trial would be, my first trial, I roll a 3, that's my trial. Just rolling it once is a trial. An experiment is having more than one trials. Normally, if you want to see if something works, you do more than one trial. Okay? So that's how we get it. So if I roll a dice 5 times to see if I get a 1, that would be an experiment because I've rolled it 5 times to help me get the probability. Now, the outcome is the result of carrying out the experiment. That is my outcome. My outcome is my result in carrying out the experiment. Next one here is sample space. My sample space can be, well, if I'm rolling a dice, it could be 1, 2, 3, 4, 5. So sample space is all the possible events or outcomes that you can have. Next one is event. Okay? So event is an event is a subset of the sample space. Okay, so it consists of one or more possible outcomes. So my event would be if I rolled it 3 times, and I could have got, my events could have been heads or tails, and stuff like that, or rolling a 2 and a 3. Those were my events. So, to donate probability, we use the term PA. This is key. This is to donate probability. Okay? So, probability of the donation is PA. Now, this means probability of A. Now, when we have a probability of A, we look at it, well, what is the probability of getting 0? That means it cannot happen. Can we have less than 0? Is there any chance that you have that you're less than 0? It's impossible. The lowest you could get is 0. Just like, can you ever be more than 100%, get a 100% chance of winning? No, 100% is guaranteed to win. There is no more than a guarantee, which is 100%. So that's why our probability must be between 0 and 1. We can't have a negative. We can't be over 100%. Next part is, what happens if probability is equal to 0? That is an impossible outcome. If the probability is equal to 0, it is impossible. That cannot happen. An example of that would be rolling a 7. If I was to roll a 7 on a standard 6-sided die, well, what is the probability of that? It's impossible. It cannot happen. There is no 7. Next one here is probability of 1. If I said you have to pick between heads or tails on a coin, well, there's only heads and tails on a coin. So the probability of that is actually 1, of getting heads or tails. There we go. And the last one is equally likely. So an experiment, if the set is equally likely, then the probability of a particular event is given by a formula. So if you can make a formula for it, everything is equally likely. So here's an example here. A fair die is rolled. What is the probability of rolling a 1? Okay? So we're going to do this one first. So here's part 1. I state the sample space. So the sample space is already stated. We have 1, 2, 3, 4, 5, and 6. There is my sample space. That's all the outcomes we could get, right? It's all outcomes. So part 2 is, what is my favorable outcome? So what is my favorable outcomes in the sample space? Well, it's only a 1. This highlighted number. Part 3 says, okay, part 3, are the outcomes equally likely? Well, is it equally likely that I get a 1 out of 2 or a 2 out of, that I get a 1 or a 2? Are they both equally likely? Yes. So yes, they are all equally likely. All right. So part 4 states, what is the probability of the event? Well, my probability of the event is 1 out of 6. And that is it. Because I have 1 out of a total of 1, 2, 3, 4, 5, 6. That is what I have. Okay, so now let's try the next one. A circular spinner divided into 4 equal sectors labeled clubs, diamonds, hearts, and spades. So it's the 4 Parts of cards. Clubs, diamonds, hearts, and spades. Look at the clubs, diamonds, hearts, and spades. When it is spun, what is the probability that it lands on hearts? So, let's look at number 1. There's 4 even spaces. So we want the sample space. We could have a club. We could have a heart or diamond. We could have a heart. Or we could have a spade. So that's my sample space. That's all I could choose from. So we're going to say they are equal sectors. It says here they are equal sectors. That's key. Now, part 2 says the favorable outcome. My favorable outcome is a heart. So it's just a heart. We're going to look at number 3. If the outcomes are equally likely. Well, it's 1 in 4 to get a heart, 1 in 4 to get a spade. They are equally likely. They're all the same amount. They're equally spaced. So yes. And what is my probability? Number 4 is 1 in 4 is my probability. Because I have 4 total outcomes. And I only have 1 that I want out of it. So it's 1 in 4. Now, complementary events. When a spinner in review B, okay, so we're just going to skip that and go on. So the event does not land on hearts is called the complement. This is very much similar to what we did in math30. So when it doesn't land on hearts, so the event that you don't want to happen is the complement. It is the event that we don't want to happen is normally the complement. It's everything else that could happen in the subset or outside of the subset that we want. So in our universal set, it's everything else that could happen. So they're complementary events. So a complementary event of flipping a heads on a coin would be a tails. That's everything else that could happen. Complementary event of this one here would be 2, 3, 5, or 2, 3, 4, 5, and 6, because it's everything else that could happen. Those are the complementary events. Next. So that's pretty much it. So basically, our complementary events, the event wanted added to the events that we don't want must always equal to 100%. Okay? So I can't say if we're rolling a die, a 2 and a 1 are complementary events. It's a 2 is part of the complementary event of a 1, but there's also a 2, 3, 4, 5, and 6. So we have a lot more. So they must add up to equal 1. This here is key. Okay? Or PA and PA naught, there's 2 ways of writing it, which must equal to 1, which is 100%. Next is compound events. Remember way back to those tree diagrams? We're bringing them back. So, here we go. Our first event here. A compound event is often used a table, a chart, or a tree diagram. Okay? So, 2 coins are tossed. And it says, the number of heads is counted. What is the probability of attaining 2 heads? Well, we go all the way down here, and we have, it says, we're just going to skip ahead, go to the tree diagram to help us do it. So, we have in coin 1, first coin we flip. We do that first. Zoom in. First coin we flip. Well, I could either get heads or tails, right? That's all I could get. Next coin we flip, we could get heads or tails. If we get heads, we can still get heads or tails in the next coin. If we got tails, we can get heads or tails. So altogether, my outcomes are heads, 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 tails, tails, heads, or tails, tails. So we have 4 possible outcomes. So what is the possibility of getting 2 heads? Of 2 heads, well, that's 1 out of 1, 2, 3, 4. That is 1 out of 4. Of getting 2 tails, that's only this one. So that's 1 out of 4. Getting 1 head and 1 tail. Well, I could do this or this. So it's 1 out of 4 plus 1 out of 4, which gives me 2 out of 4, which is equal to 1 out of 2. That's how we do that one. So here's an example. Now we're going between a spinner and a head, and flipping coins. Okay, so complete the tree diagram, show all the outcomes for the experiments. Let's complete the diagram. So here we could go heads or tails, heads or tails, heads or tails here. And if we get through, we could go heads or tails. Now here again, we have heads or tails, heads or tails, heads or tails, heads or tails. So these are all my possible outcomes. I could go 1, tails, heads. Or I could go 1, tails, tails. Or I could go 2, heads, heads. Or I could go 2, heads, tails. Or I could go 2, tails, heads. Or we could look at this one, 2, tails, tails. Or we could go 3, heads, heads. Or 3, heads, tails. Or 3, tails, heads. Or 3, tails, tails. Okay? So basically what happened here, we're doing 3 different events, and we want to know the probability of all of them. So we have the spinner, then we do coin 1 and coin 2. So we have 3 different things, so I reorganize it in a tree diagram, which makes it nice. Normally when we have 3 completely different things, tree diagrams work wonderfully. So here we go. Complete tree diagram, we're done. How many elements are in the sample space? Oh, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. There are 12 elements. Show how many you can use the fundamental counting principle to answer question B. Well, fundamental counting principle. So basically, I have 3 options for the first one. That's 3, right? That's my first one. I have 3 different options. I have 3. Then I have 2 options, and then I have 2 options. And it must be in that order. So it's 3 times 2 times 2. There's our fundamental counting principle. That's how we could do it. That equals to 12. Hey, that works. Because we have spinner, we could get 1 or 3. 3 options. For coin 1, we could get either heads or tails. There's 2 options. This one, we could get heads or tails. Another 2 options. Huh. Are all the outcomes equally likely? Well, yeah, they are. Yes. State the probability of attaining 3 head, or a 3 and 2 heads. So we want a 3 and 2 heads. That's only 1 out of 12. Okay? A prime number and exactly 1 tail. Oh, prime number and exactly 1 tail. So if we look at this, we're going to say 2 and 3. We're going to use those as our prime numbers. 2 and 3. 1 isn't quite really a prime number. So prime number is exactly 1 tail. So I have 1 here, and I have 1 there, 1 there, and 1 there. So I have 4. So that is 4 out of 12, which is the same as 1 out of 3. Okay? Here we go. Now, last one, and we're done. And you could, I'll see you tomorrow, and we work on the assignment together. A blue die and red die are rolled. The outcome 3 on the blue die and 4 on the red die can be represented in the order pairs. So here, every time we're using die or numbers, we tend to make a grid like this. Okay? So show all the possible outcomes. We could go 1, 1, 2, or 2, 1, 3, 1, 4, 1, 5, 1, 6, 1. Now here we go 1, 2, 2, 2, 3, 3, or 3, 2. Are you making mistakes? 4, 2, 5, 2, 6, 2. Here we have 3. Oops, 1, 3, 2, 3, 3. And here we're going to have 4, 3, 5, 3, 6, 3, and 1, 4, 1, or 2, 4, 3, 4, 4, 4, 4, 5, 6, 4. I'm just going to finish this out. So there we go. Now we have that done. Okay. So how many points are in a sample space? Well, if we look at this, this is a 6 by 6 grid. So we have 6 by 6 grid. So that's 36. So is there another way of doing it? Well, we have 6 options for the first one and 6 options for the second one. So there's 2 different things we're rolling. And we have 6 options for the first one multiplied by 6 in the second one. Same thing as there, except this would be very messy and be a huge factor. Okay, list the events. The same number appears on each die as a subset of the sample space. So list the same number appears on each die. So we have 1, 2, 3, 4, 5, 6. So we have a 1, 1, we can have a 2, 2, we can have a 3, 3, and we can have a 4, 4, and we can have a 5, 5, and we could have a 6, 6. So there's the sample space. Okay, now it says, state the probability of the following events. The same number appears on both dice. So we have 6, there's 1, 2, 3, 4, 5, 6 outcomes out of a total of 36, which is the same as 1 and 6. So a different number appears on each die. Well, that's every other outcome. So that's every other outcome besides that, that's going to be our complement. So it really wants the complement, which is 30 out of 36, which gives me 5 out of 6. How can answer B help to determine, or the second determine the first one? They are the complement. Or I could have added them up. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. So there's 30. So 30 out of 36. So these are the complements of each other. So I'll see you tomorrow and we'll work on the assignment together. Thank you very much for watching.